Hello and welcome to the first video we're going to be doing on how to solve word problems in physics. Um, Many people would advocate using equations or the such, but we've been working with graphs a lot, so we know how to work with graphs. So what we're going to do today is take a look at how we can use graphs to solve problems, even when we're not given one. So for instance, an airplane, it's Boeing 747 to be precise, needs to get to a speed of 184 miles per hour, which I've already converted for you to 82.26 meters per second to take off, assuming the plane starts from rest, has a constant acceleration, and takes 25 seconds to take off. What is the acceleration, and how far does the plane go on the runway before taking off? So the first thing I like doing with a problem like this is I like going through and highlighting some of the key numbers or point out some key facts. So it says a speed of 82.6. It says it starts from rest, which is always a keyword we want to pay attention to. Constant acceleration isn't so much a phrase that we care about, but it tells you that there's no curve. We can actually use our kinematic understanding. AKA, there's going to be a straight line acceleration, and it takes 25 seconds to take off. Okay, all this information kind of gets meshed together, and the first thing we need to do here is make a graph to understand it. Typically, when we're asked to make a graph, what we want to do is we want to make a velocity time graph. So we're not going to make anything particularly great here, just rough eyeball. Okay, over here we're going to do velocity, like so.
Minor mistake here. The velocity unit should be meters per second.
As time goes on, the plane's going to speed up. Now, the important thing we need to mention here, though, is it starts from rest. Rest is a keyword to mean it starts from 0. And then it's going to continue upwards. What the exact slope is, we don't know. But it's going to end up looking something like this. Once we've got this drawn, we can go, okay, well, we need to find two things. We need to find the acceleration, which I'll do in blue. And we need to find the how far, which is a fancy way of me saying the displacement. So to start, we'll start with the blue. We have a velocity time graph and we want to find the acceleration. Thinking back, acceleration is the slope of a VT graph. So we just need to find the slope. I know that this point here at the bottom is 0, 0. And I know this point up here is 25, 82.6, or 82.26. How did I get this? Well, it starts from rest at time 0, and then it starts moving. And at time 25, it takes off. So this is 25, 82.26. So at that point, it's just finding slope, which thankfully, y2 minus y1 is really simple. 82.26 minus 0 over 25 minus 0, which gives me, grab my calculator for a second, an acceleration of 3.29. 82.26 is in meters per second. We get that from up here. 25 is in seconds, so this would be in meters per second squared. And there we go. Using our graph and understanding of how this works, we built a quick and easy thing. Now, as for the second part, which we'll do here in red, we'll want the displacement. Now, for a velocity time graph, we said the displacement is equal to the area. So it's this. We have a triangle here. So in this case, our area is going to be 1/2 base times height. Half doesn't change, it's a constant, but my base is 25. How did I get 25? Well, it's the time, 25. Alternatively, 25, 82.26 is here, which means that this side here is 25 long. And the y-axis here is 82.26 tall. Multiply all that together, I get 1,028.25 meters for my displacement. And that's how this goes. Step one, make a passable, if not always amazing, graph. Step two, solve the problem based on the details you got. Let's go ahead and clear this off and take a look at another one. Let's take a look at another one. Imagine you're driving down the road at 33.53 meters per second. That's about 75 miles per hour when you spot a cop ahead of you. The local speed limit is 24.59 meters per second. Speeding much. 55 miles per hour. Your car can provide a constant acceleration of negative 3.55 meters per second squared, which means that you can slow down at that rate. How long does it take you before you slow down to the legal speed, and how far do you travel before you reach legal speed? Okay, let's go ahead and start by underlining some important numbers here. First things first, I see this 33.53. This acceleration is going to look pretty important. This 24.59 also looks pretty important. The first thing I want to address before I address any of the numbers or draw on a graph even is the fact that I am talking about a speed here, but we solve problems using velocity, or make velocity graphs. The reason this works in this particular case is when you're driving your car, you're traveling it in a relatively straight direction. And on a particular given stretch of road, you're not going to swerve or turn too much. In fact, most roads around here are relatively straight. Most roads around here are relatively straight. You're not going to curve or that. You're effectively traveling in a straight line. And if you're traveling in a straight line, your speed and the velocity are the same. The reason we can do a problem like this is because of that assumption. Now, this won't always be true. We'll talk about some circumstances where it isn't, but for now we can use that cheat. That said, let's go ahead and talk about this. So let's make our graph. All right, and you're going to start, put this in red, you're going to start traveling at a certain speed, and then you're going to slow down. Now notice how you're not slowing down to a stop. You're still going fast, just not as fast as you probably wanted. So then you're going to end here. And the first question is how long? So we want to know what this t is here. And the second thing we want to know is the distance. How far do you travel, or the displacement more accurately. So let's go ahead. So how far is, again, another way to say displacement. So we're asking about this area. Let's go ahead and do these two problems in order and go from there. So how long tells me time. I need to know what the time is. Well, the time is right here. It's on this axis. Totally works out. If I could just find out that axis, that'd be great. Unfortunately, I don't have that. All I have is these two different things and a line connecting them. But I do know that the slope of this line is negative 3.55 meters per second squared. I got that from up here. And if I remember correctly, that's also my acceleration, and acceleration is my change in velocity over my change in time. Change in time is a great way to say how long. So all I need to do is have my change in velocity and my acceleration. Now you could plug in your numbers, but I personally like solving symbolically. It makes my life certainly easier. So what I'll do is I'll put a 1 there, and then I'll cross multiply. A times delta t equals 1 times anything is that thing, so delta v. Which means that now I can go rearrange this and go, okay, well, I'm solving for t, so delta t equals delta v over a. Okay, cool. Let's plug in some numbers then. Delta v, delta is always final minus initial, so it's my final velocity minus my initial velocity. In this case, that is going to be 24.59 minus 33.53. You'll notice I'm using the meters per second and not the miles per hour. There's 3 reasons for this. Number 1, it's a science class. Use meters per second. Number 2, this is in meters per second per second. So I want the units to match so that they cancel out, leaving me with seconds. And the third and kind of most arbitrary of the reasons is that a lot of the things on the AP exam are going to be meters and seconds. So the people who are going to take the AP exam need the practice. That said, if you don't have the AP exam, sorry, you're suffering for their sake. My acceleration is negative 3.55. Now this all here looks messy, but it's just algebra. Subtract on top, then divide. So put it in your calculator, and you'll get 2.55. And because we're talking about time, it's almost inevitably measured in seconds. And there you go. Easy peasy. Now, granted, if you slam on your brakes and get 2.55 seconds to slow down, I'm sure the cop's going to notice anyway. So you might want to go a little easier on that than that, but that's the time. The second part of this problem is this. It's asking about this, how far, this area on the inside here. Now, there are 2 ways you can go about this. The first is to split it into parts, like so, with the triangle up here and the rectangle down here. I personally think that's a great idea. We have our time, we solve for it right here in purple, so we can use that. The other way we can do is a trapezoid. I'm going to do both ways, you can take your pick. So let's start by splitting. So we split here, like so. Let's talk about this rectangle first. This rectangle is how wide and how tall. Well, the lowest point here, this point right here, we know is 24.59 meters per second. How do we know that? Because it's what you slowed down to. Comes out of the graph. So this side is 24.59. So the rectangle has an area of 2.55 times 24.59. To that, we've got to add the area of our triangle here. Now, this gets a little messy because while it is still half base times height, my base being 2.55 seconds, the height of this triangle is only from here to here. It's only the difference in my velocity, which would be, in this particular case, the 33.53 minus 24.59. This little sliver here is the height of the triangle. We're not going to use the entire height because the triangle isn't that tall. The triangle is only this tall. Do all that, check your math, and it will equal out to your answer. Go ahead and plug it in your calculator, and you should get 74.10 meters. That's one way you can do it. And it's a fairly confident and solid way, but what I would rather do is I'd rather go back and go about it in a slightly different way. So instead of going about it as a rectangle and a triangle, let's go about it as if it was a trapezoid. Now, this is not going to be on an equation sheet. This is not common knowledge for the AP exam, but it is a valid way of doing this. And for those of you who've forgotten, the area of a trapezoid is 1/2 height times base 1 plus base 2. The bases are defined as the sides that are parallel to each other. So in this side, it would be this side, which is straight up and down, and this side here. Granted, this would work better if I could actually draw. Let's redraw this graph right here. I draw this graph carefully for a change. We can see that these two sides here are parallel. So this would be my B1. This would be my B2. I personally prefer the trapezoid because it's just quicker and easier, but it's a lot harder to visualize for a lot of people, so I don't always encourage it. Regardless, once you've got it, 1/2. The height is the distance here between these 2 points, which we solved for previously, 2.55 seconds. My bases are my two different velocities, 24.59 plus 33.53. And if I plug that in the calculator, I will once again get the same number of 74.10. And there you have it. Let's take a look at one more practice problem. Okay. Julian is walking east at 5 meters per second when he hears a bear behind him. Fearing for his life, he takes off in a sprint, continuing east and accelerating constantly at 1.11 meters per second per second. After 5 seconds, how fast is he going and how far has he traveled? Give this one a try on your own and then check back in. Okay, like all these problems, we're going to start by drawing a graph. So just quick, sloppy brushwork. Looks something like this. Time is going to be in seconds. V is going to be in meters per second. I mean, Julian, our guinea pig for this problem, is going to start traveling at 5. Well, 5 is not 0, so I'm going to start up here. And then I'm going to continue on speeding up. Up means I'm getting faster to here. Now, I don't know how fast I'm going here, but I do know that once I am here, the problem stops. So this point here is t, and that is 5 seconds. But from this, I also know that he is traveling initially at this 5 meters per second. So this point here is 5 meters per second. From this, I need to know after the 5 seconds, how fast is he going and how far has he traveled? Well, let's start with how fast in blue. I don't know where this point is. I don't know how high it is. I just know it's after 5 seconds. But it's on this line that starts from the 5 meters per second and continues upward, and it follows this acceleration. So when in doubt with one of these, go to your acceleration definition. A equals delta V over delta T. In this case, A is 1.11, and V, delta V is V final, which we don't know, minus V initial, which we do. And then delta T, in this particular instance, is 5. Move the 5 to the other side, I get 5.55 equals V final minus 5, because that is my initial starting point right here. Move that to the other side. We get V final equals 10.55 meters per second. So at the end of this, Julian's going 5.5 meters per second. The second step is to find the area. Again, there are two ways to do that. You can do the triangle and the rectangle, or you can do the trapezoid. Either way works. I'm going to do the triangle and the rectangle this time. So the area of my triangle plus the area of my rectangle equals area total, which equals my displacement. The triangle is half base times height. And the rectangle is just base times height. So in this case, the base of my triangle is 5 wide. It's 5 seconds wide. My height here is this one right here, which is the 10.55 minus this 5 off the base, or the 5.55 I had originally for my delta V. And then my rectangle is 5 times 5, which would be 25, but just for sake of completion, write out the steps. Which means the only thing I have to do is that half times 5.5 times 5, which gives me 13.89. Add the two of those together, and I get my displacement is 28.89 meters. And there you go. The hardest part about this is probably going to be drawing the graphs and working through them. So take your time, ask your questions, and have a good day.